All right. So this is our last lecture of the semester. And so what I decided to do for the last lecture is a fun lecture. Because none of the others were fun at all. No, I decided to do an optional lecture, and it's optional even in the sense that you won't be. I'm not going to test you on this material. You're not going to have homework on this material, but it's a fun extension of some of the ideas that you encountered earlier in the class, and that is the subject of transfinite induction. Okay, so we learned about induction at the beginning of the class, and one of the things I hope you've come to realize about introductory analysis is it's really a lot about wrestling with the infinite, right? We know how to work with finite sums, but what do you do with infinite sums? We know how to deal with discrete functions, but how do you deal with continuous functions? Okay, and how do you, at the very beginning of the semester, how do you count? So that's the subject that we're going to wrestle with today. So the first thing we have to learn about is how to count, and that's the subject of ordinal numbers. And once we define ordinal numbers, then we'll be able to say what it means to do transfinite induction. Induction, if you recall, is basically a way of reasoning about a whole family of statements. Right? How many statements? Well, countably infinite many statements, right? And so what transfinite induction will allow us to do is to reason about a whole family of statements where the set of statements might be possibly uncountable, okay? So, but let's first talk about ordinal numbers. So this is really the question of how to count. How do we count? And I'm not going to repeat one of the earlier lectures, but we're going to try to think about counting in a sort of more general framework. So the first thing that I want to do is talk about orderings, and then see if this might give us a way of counting. So suppose I have a set X with an order on the set, and maybe another set Y with an order on the set. So you might think of this as, an example might be the real numbers with the usual ordering, or the natural numbers with the usual ordering, or a set of vectors with the lexicographic ordering. Okay. Well, let me define what I mean by an order type. I'm going to say that these two things have the same order type if, take a wild guess, these are ordered sets. We'll say they have the same order type if there is a bijection between x and y that preserves something, the order, okay? So most of the functions in math are interesting because they preserve something, right? In this case, preserving order. So let's say these have the same order type if there exists a bijection f from x to y such that x less than y implies f of x is less than f of y. Okay. All right. So this is, in fact, the if and only if. Okay. So we call this thing, it preserves order, an order isomorphism. And it preserves order. So this is just a way of saying these things look the same from the point of view of orderings. Okay. Now, we've learned about one type of ordering already, and that is something called a well ordering. Who can remember what a well ordering is? So X is well ordered if careful, this is way before we defined compact set. If every something has a something. Well ordered? if every, did we define this earlier, well ordering? If every has a okay, so least element, if every subset has a least element, or every non-empty subset has a least element. Okay. Okay, that's what it means to be well ordered. So, for instance, are the real numbers with the usual ordering well ordered? No, because you could take an open interval and that's a non-empty subset, does not have a least element. Okay. Are the integers well ordered? Yes. Are the careful. Are the natural numbers well ordered? Yes. Are the integers well ordered? Give me an example of a subset that doesn't have a least element. 2z, right? All the even integers, for instance. Okay, good. Okay, why did we learn about well ordering way back when? Because it enabled us to do induction. Very good. So we're going to need to develop a concept of well-ordered, good concept for well-ordered sets for in order to do transfinite induction. Okay. Okay. So what I'm going to present to you is a theory of ordinal numbers, and this is due to von Neumann, 1923. Theory of ordinals. Actually, Georg Cantor sort of developed the beginnings of the theory of ordinals, and what I'm going to show you is sort of a slick version due to von Neumann. And the idea here is to basically this helps classify the well-ordered sets. Okay. Okay, so here's how it goes. This is quite cool. I mean, what's a well-ordered set? What's a well-ordered set look like? I mean, before I even just do this construction, let me just give you a sense of what it's good for. Here's a set. I can think four things. I can think of it as being well-ordered, right? Everything to the left is smaller and everything to the right is bigger, yes? Every subset has a least element, yes? Good. Let's see. 4 elements. What about, the natural numbers? Well, that's a set that kind of looks like this, doesn't it? Etc. Right? Dot, dot, dot. Yes. Okay. Well-ordered, yes? Okay. But there are other well-ordered sets besides this, right? There is, for instance, how about this one? How about the natural numbers that go on and include all the ones it did before, and just to make things interesting and make sure that they all fit on the board, I'm going to make them get closer and closer on the board, but think of these as just points, yeah? Closer and closer. And then, right at the very end, after you do all natural numbers of them, I put another element there. Is that a well-ordered set? Yes, it is. Every subset is a least element, yes? Okay. What if I, from here, decide I'm going to just start to put another point here? Is this well-ordered, this whole set? Yeah. In fact, take every subset as least. Oh, okay. What if I do this? Well-ordered? Yes? Oh, what if I add in a few more points and just keep going then? Dot, 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 dot. In fact, suppose I do the same thing here and then keep going for another natural number collection of sets, indexed sets. And then, I didn't bring my colored chalk. Suppose I add in yet another point right at the end here. Is that well ordered? Okay, so there's lots of kinds of well-ordered sets. Are these order isomorphic between this, let's say, 2 sets of natural numbered sets with a few dots at the end of it? Is it order isomorphic to this? No, there's no bijection that will preserve order. Okay? Okay, so there's lots of well-ordered sets, and von Neumann asked, well, can you give me a way to classify all possible well-ordered sets? Okay. How many points do we have in this set? Finitely many. How many here? Countably many. How many here? Also countably many. There's countably many here, another countably many here, and 3 more points here. Right? Okay, so there are, in fact, many different well-ordered sets that have the same cardinality. Right? Okay, so what was von Neumann's idea? Well, von Neumann said, well, look, here's one way we could start off. Let's start off by describing a set that we'll think of as the set, a well-ordered set. It's a set that's naturally, vacuously well-ordered. The empty set. Okay. Okay. And then, okay, what's another set that I might want to consider? Well, how about the set containing one element, right? Or the set containing 2 elements. Now, you could just create your own sets that have, set containing something and set containing something else. But it sure would be nice if I could maybe write all the other ones in terms of ones I've defined before. This was von Neumann's idea. So what we're going to do for the next ordinal is to basically look at the set containing the empty set. How many elements does this have? 1 element, and the element is the empty set. Okay. Oh, very cool. Now, what am I going to do next? Well, I now want a set with how many elements? 2 elements. So what elements would you suggest? No. Well, you could. Yeah, let's take the union of all the objects that we've defined previously. So that's the set with 2 elements, and it's basically the previous 2 things. Yes? With me? Okay. What about a set with 3 elements? We're going to do this one, and one more. But that one more thing is this one and this one. Right? Happy? How many elements does this have? It looks like 4, but it's really 3. This, and this. Yes. Ooh, excellent. Haven't gotten there yet. But I've actually written the ordering in the way that's suggestive of the order. Can you guess what the ordering might be? Oh, no, don't say number, because we haven't defined number. Yes, less if it's contained. So containment is going to be the ordering. Okay. Very cool. So you could, if you want, think of this ordinal number as something that's 0-like, right? And this is sort of the ordinal number with 1 thing in it. This is 2 things. This is 3 things. But I'm not counting sizes, because that would be a cardinal number. Ordinal numbers are sets that are they reflect also the order type, right? A well-ordered type. Okay. Good. So yes, keep going. So some things to notice here with this construction is that every member of 3 is a subset. Okay, so every member of one of these ordinal numbers is a subset of one of the ordinal numbers. Would you agree? Let's see. 1 is a subset of 2. Yes. Yes. Is 1 a subset of 3? Yes. Very good. Is 0 a subset of 3? Yes. Okay. Is 3 a subset of 2? No. Okay. So that's in fact we're going to order the sets by membership. or containment, as Willie referred to. Okay. So, here's our definition of an ordinal. An ordinal is, this is quite cool, a set that is two properties. First property is we're going to demand that it be transitive. Sometimes this is called or complete. Every member is a subset. Okay? Is that true? Is every member here a subset? This is actually almost tautologous, but it's not quite. Is it true that this is a member? Yes, that's a member. The set contained the empty set. Now, is it a subset? Yes, because the thing that's in it is here. Right? Yes? Okay. Is this thing a member? The set containing these two things? Yes. Why? Well, it is a member because it's in here. Is it a subset? Yes, because both these things are here. Okay? Okay, so every member is a subset. That's what we see here. Okay? Every member of 3 is a subset of 3. Okay, and so an ordinal has a property that every member is a subset, and the second property is it's strictly well ordered by membership. Okay, so I can well order each of these sets by the things that are members. Okay, so from this definition, it's a very innocuous definition, there's a lot that comes from it. You might wonder, well, what do the ordinals look like? What other things are ordinals besides the ones that are the obvious ones here? Oh, well, check this out. The first property you might notice is that if alpha is an ordinal, then I can define a new ordinal very simply by, I'll call this the successor of alpha, S of alpha. I'll take the set alpha and union it with the set containing the set alpha. Okay? The claim is that if alpha is an ordinal, this new construction is an ordinal. And it has a name. It's called the successor ordinal. Okay, let's see if we buy that here. Let's see. If I take 2 and I union 2 with the set containing this set, don't I in fact get this? There's the original set 2, and I union it with the set containing this. Do you see that here? Each successive thing you get is basically throw in this, take this set and union it with the set containing this set. Okay? Happy? Okay, that's one consequence we see. The successor of alpha is an ordinal. Okay, here's a second thing we notice. If alpha is an ordinal and beta is in alpha, remember alpha is a set, what can I conclude about beta? If it's an element of alpha, yeah, well, the claim is if alpha is an ordinal and beta is in it, then beta is also an ordinal. Does beta have this property that every member is a subset? Yes. Look at this creature. It's in alpha, but is every member a subset? Well, yeah, of course every member is a subset. Because the members of this thing are these two things, and they actually are subsets. The empty set is subset. This is a subset as well. and it follows from these properties. Why? Well, because every member of the original thing is a subset. Okay. Let's see. Here's another thing that we might notice. Suppose you have a whole set of ordinals. Suppose big A is a set of ordinals. Well, it's easy to verify. Here's another way you can get a new ordinal. You give me a bunch of different ordinals, like, how about this one? This one and this one, 1 and 2. Here's a set of ordinals. Or here's another set, 0, 1, and 3. That's a set, yes? Well, one thing I could do to create another ordinal is to take their union. And we have a special name for their union. We call it sup of A. It's defined to be their union of A. I won't go into what sup means because you already have seen something like this before. We can think of this as a kind of supremum. What's it doing? It's taking the union of these things. It's an ordinal. Ah, interesting. Okay, so what does this mean? Are there any other ordinals besides the obvious ones? Well, yeah. So let's see. So this is I should just say what von Neumann's theorem here is. So it turns out you give me any well-ordered set, I claim any well-ordered set is actually order isomorphic to one of these, to some ordinal alpha. So sorry, that's to be more precise, to some ordinal. Like, for instance, this thing. It's order isomorphic to the successor of 3. This thing is order isomorphic to, well, I haven't given it a name, but how would you define this in terms of things you might already know? The sup of all the finite ordinals, right? It would be the sup of 1, union 2, union 3, union 4, union 5, that construction. Okay, we actually do have a name for that. It goes something like this. Let's see, if I could order the ordinals. 0, 1, 2, 3, 4. Okay, starting there. I'll just keep going, yeah? And each time I'm taking a successor, aren't I, right? But you could imagine then, okay, finish taking all those successors. That gives you a set of ordinals. But now you can do a new operation, which would be take the sup, right? That sup is the order type of the natural numbers. And so we have a name for that ordinal, the one that lives after all of these. After all of these, we give it a name. We call it omega. Okay? So it's the first infinite ordinal. It's countable. Okay? It's not finite, and it's clearly, you can, every element in it can be put in bijection with the natural numbers. Okay? The other thing I want you to notice is it's the first example of something that's, well, okay, except for 0, it's the first example of something that's not a successor of anything. It's given by the supremum construction, so it has a special name. We call it a limit ordinal. A limit orbital is not the successor. Is not S of alpha for any alpha. It's not a successor ordinal. Okay. Oh, okay. Okay, well, let's see. What happens after you get to omega? Well, the next ordinal is... Yeah, that's a good name. When you throw in an extra point, that's called omega plus 1. What is omega plus 1 really? It's, yes, a successor of omega. It's actually also the supremum of all the things preceding it. Okay, Willie?
I'm wondering why omega is not order isomorphic to omega plus 1.
Oh, it's not order isomorphic? Because the picture of omega is like this. And we think of the next thing as the union of all the things previous to it. And the picture of omega plus 1 is this thing with one more thing.
Well, I guess my question is, if they're both countable, then they have the same cardinality. So it's hard for me to intuit how they can be different.
Yes, they have the same cardinality, but they're not the same ordinals, because the ordinals have an order. When you talk about cardinality, all you're interested in is their bijection. But for order order types, you're interested in also preserving order. So there is no way you're going to make a bijection between these that'll preserve the order. Right? So tell me where you're going to send. I mean, where are you going to send this point? Well, it has to be bigger than everything else. Yes. So you better send it to something that's bigger than everything else. So this point, if there were such an order isomorphism, this point would have to go here. But then where does this point have to go? The next one down or something, right? But wherever this gets sent, you'll miss some, and then you're in trouble. Okay? Not the same order type. Great question. Okay, but, we can keep going. So the next ordinal after that we'll call omega plus 2, which is basically this picture with another dot. Yes? Omega plus 3, omega plus 4, ... And then... Yeah, what do you think we call this thing with the white and the green points? Yeah, actually, for various reasons, we don't call it that. We call it omega times 2. Because it's omega, if you like, we write omega plus omega, and we write omega times 2. It means do omega order type first, and then do another omega. Okay? This is not the same as 2 omega, which would be omega many 2's. So omega many 2's would be do 2, and then do 2, and then do 2. Yes? Whereas omega times 2 is do omega, and then do omega. Yes? How they're not order isomorphic? What do you think 2 times omega is an order isomorphic to? Look, I've got a bunch of points here, a bunch of points here, a bunch of points here. They're not order isomorphic because the limit ordinals, there are 2 of them here. Where are you going to send this limit ordinal, this one? Well, if you send it anywhere in this construction, there's only finitely many before. Whereas in this construction, there are infinitely many before. Okay? So in fact, 2 omega, believe it or not, is actually equal to omega in ordinal arithmetic. Okay? But it's not the same as omega times 2. Okay? So 2 omega, omega 2. So in ordinal arithmetic, multiplication is not commutative. Right? Okay, Rebecca.
So if you do an entire omega and then an entire omega, and then another omega, is it omega times 3?
Yes, it's omega 3. This is omega 2 plus 3, because I put 3 points there. Okay? Yeah, so you can keep going. Go crazy. Here we go. Plus 1, plus 2, dot, dot, dot. And then the next one, if you could go beyond that, take the soup, and you get omega 3. And then, okay, omega 3 times plus 1, omega 3 plus 2, dot, dot, dot. And then you get what? Omega 4. Oh, and then after a while, you get omega omega, which we call omega squared. Yes? That's okay. And then omega squared plus 1, omega plus 2, blah, blah, blah. Past some point, you get omega squared plus omega. That's all right, yes? Etc., dot, dot, dot. Eventually, you get omega cubed, omega to the 4th, dot, dot, dot. Eventually, and take the successor of all those, you get omega to the omega. These are all countable. These are still all countable, okay? Then, keep going, omega to the omega plus 1, omega to the omega plus omega blah, 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 dot, 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 okay. Eventually, you get omega to the omega to the omega. And then you get omega to the omega to the omega to the omega. Still countable. Large, but countable ordinal, okay? And eventually, past all those points, you get to something we call epsilon naught.
Wait, when did the permittivity of free space get here?
Yes. Yes. And omega naught is defined to be the first ordinal. What? Epsilon sub naught, yes. Is defined to be the first ordinal that satisfies the property. The ordinal epsilon naught is omega to the epsilon naught. So this is really, if you like, it's omega to the omega to the omega infinitely many times. Okay? Countably infinitely many times. Okay? But there are many such ordinals that satisfy this property. So after a while, you get to omega, you get epsilon 1, which is also satisfies this property, but it's not the first, but the second one that satisfies this property. Right? Okay? Etc. Dot, dot, dot. These are all still countable. Countable ordinals. Yeah. Okay, so eventually then, you get to, past all these, you eventually get to the first uncountable ordinal, which we call omega 1. Okay. Then you can do omega 1 plus 1, et cetera, et cetera, et cetera. And keep going. Okay, don't be fooled. Don't be fooled. This is not the same thing as, we haven't just, by listing all these ordinals in a sequence, somehow proved that uncountable ordinals are countable. We haven't done that, right? Because when we said you can list things in a sequence, we really mean you can put it in an order type that's isomorphic to the natural numbers. But here we have some, lots of limited ordinals in between. Jenny. Interesting question. Very interesting question. Well, so all we said here was we just defined an ordinal to be the set of satisfying these properties. So, the first uncountable ordinal is basically, just like every other thing in this list, the supremum of all the things that preceded it. You can't stop me from taking the supremum of all the things that preceded it. And you can verify that, just by verifying property 3, that if you take the supremum of a set of ordinals, you'll get something that is an ordinal. Well, there has to be a first uncountable ordinal. Well, if you look at all countable ordinals and take their supremum, that has to be an uncountable ordinal. because it's not going to be every member. Every member is a subset, and it would be very silly if you took the set of if you took all uncountable ordinals and you took their supremum, and somehow that was a subset of one of the things that was already in the list, because there's other things in the list. Willie?
I'm wondering if there's not some greatest element below omega 1, is there?
No. Omega 1's a limit ordinal. Yeah. Yes, okay. Now, of course, if you ask me too many questions, you're going to reach the limit of my understanding of set theory. But yes, Lindsay.
I was just gonna ask, you're writing these down in a certain order. Like, obviously, you're not writing everything down, but like.
Thank you.
But like, you're putting like a defined, like you're enumerating them basically, and can't you not enumerate uncountable things?
Yes, but when we say we can't enumerate, what we really mean is we can't place into a bijection with the natural numbers.
But like in between every one of these, like omega and 2 times omega or whatever,
Yeah.
can't you put that in a bijection with the natural numbers?
Yeah.
Couldn't you put each one of these dots that you have there in a bijection with the natural numbers?
Yeah.
So then how do you eventually get to uncountable?
Well, yeah. So, I mean, the thing that's not clear from this is that there are. It's not clear to me either. Apparently, is that there? I mean, I think I hear what you're saying. You're worried that you can do some kind of enumeration where you take, okay, if I wanted to enumerate this, I'd take the first thing from every thing, second, and or do some kind of snake-like argument like we did for the rash. Yeah, you can't do that because there are I mean, okay, so look what happened. You want to do what you did. You would do that with, okay, the first omega, the second omega. So you go omega, omega 2, omega 3, and by the time you get to omega squared, you have that array that you could snake through. But there's way more stuff, right? And these all accumulate on each other in very funny ways. And so you won't be able to actually write out an enumeration if you tried of the things that are of any ordinal that's less than omega 1. Of omega 1, the things that are in omega 1. There's just too much here that's accumulating upon. I mean, you have a bunch of, this thing is a limit ordinal, but it's not only the limit ordinal of the things preceded, it's also limit ordinal, it's like a limiting ordinal of a bunch of limit ordinals. So it's really, what's happening here is really weird, okay? It's hard to convince you of that, but okay. So here's another thing you can actually say, and it's a version of the library paradox. You can't talk about the set of all ordinals, because if you could take their supremum, and that would have to be an ordinal, and then it would be somewhere already in the set, and then that, yeah. So you'd run into problems. So, the Russell's paradox. Define. Look at the catalog that contains the. Look at the catalog that contains the library catalog that contains how's it go? Every book. Look at all the sets that contain themselves. Sorry, I was trying to say this in terms of library books and stuff. The catalog that contains every book. Yeah, look at the sets. Look at the set of all. Look at the set that contains every set that does not contain itself. Is that a set? Well, if no, then yes. If yes, then no, and you run into problems with set theory. Yeah. So the way around that is, well, it's not a set. You have very careful ways to construct sets, and similarly here, you can't talk about the set of all ordinals. It turns out to lead to a contradiction. So you could talk about the class of all ordinals, but not the set of all ordinals. Okay. Good. So we've at least given you some sense of what an ordinal is and that there are lots of them. Okay, so let's talk about induction. So let me just have you recall when we talked about induction. How did we define it? Well, we used the principle of induction. And I'm just going to give you a version that's strong induction. It'll be the one that's most useful for us. So I'm going to let S sub n be what's called the section. So it's the set of all numbers in the natural numbers. This is just for regular induction, where I is less than n. It's called a section. So it's everything previous to n. And our definition was that A in n is inductive if we called a set inductive if for all n in the natural numbers, if the section is in the A, then what do we conclude about the set A? We call a set inductive if everything previous is in A, then n is also in A. That's what it means for a set to be inductive. Okay, so if the fact that everything less than n is in A means that n is also in A, we say A is inductive. Okay, and the principle of induction or strong induction basically says if you have an inductive set in the natural numbers, what can we conclude about A? It must be all the natural numbers. So just take the set, for instance, of all indices for which your family of statements it holds. Really, induction amounts to showing that the set is inductive. And the principle of induction says if it's inductive, it must be the entire set of indices. Okay. Let's see. Let's recall the proof. This is also something we did earlier. Why is it that if a set's inductive, it must be all of n? Well, remember, this is by contradiction. If A was not all of n, then there must be a smallest element that's not in A. Then n minus A has a smallest element. Oh, okay. Right, so that's our picture here, right? This is our set. And if I look at all the things that are not in the set, let's say this is A. All the things, there's a smallest thing. What's the contradiction? And it might say has the smallest element. Let's call it n. So what's the contradiction? Little n, yes, Emil? Oh, but everything before it is in A. Therefore, n is in A. Contradiction, right? But then Sn is in A, which implies that n is in A. Contradiction. Okay, great. That's the principle of strong induction. Well, we're just going to do exactly the same thing now for sets that are well-ordered but not necessarily finite or countable, or not necessarily n, the order type of n. So here's the theorem that we're going to rely on. It's the following theorem. Every set, I claim, can be well-ordered. And the proof, I'm not going to do, but you can look up, basically depends on the axiom of choice, or something called Zorn's lemma. If you take an algebra, you've probably seen Zorn's lemma. And the axiom of choice is this interesting axiom which says if you've got a possibly infinite collection of sets, you can form a new set by choosing, that's why it's called the axiom of choice, one element from each of the sets in the collection to form a new set. Seems very harmless, but it leads to very interesting results. So, what's great about this? Well, what's great about this is you give me any set you like, I can place a well-ordering on it. If I can place a well-ordering on it, I can use induction, transfinite induction. So here's what we're going to do. Let's well-order the set of statements we're trying to prove. Okay? Or the well-order the index set. Okay, let's call it J. Then everything I said above is going to hold, except I'll just call S sub alpha the set of all indices gamma, where gamma is less than alpha, a section. And we'll call a set inductive. What's that going to be? Well, inductive means for all alpha in the index set, if the section is in A, then alpha is in A. Just like before. And now the principle of transfinite induction. What's a principle of transfinite induction going to say? Suppose J is well ordered. Then A in J inductive implies what? A is all the index set. So that basically all the statements are true. If you can show that any section of indices, for those statements are true, that implies the next one in the well ordering is true, then all the statements are true. So it's basically allowing me to induct on this ordering. If I can show for any creature here, everything before it, those statements are all true, then this one is. Then, if I can show that, then the statement must hold for everything in the index set. Yes, Paul.
What do you mean by every set? Because I thought we were discussing earlier that, for instance, the open interval, which we could write as a set, is not well ordered.
It's not well ordered with the given order, but we can find an order that will turn the set of real numbers in the interval 0, 1 into a well-ordered set. Yeah. Now, of course, the axiom of choice is, this isn't a constructive argument, right? So, I mean, nobody can give you an explicit well-ordering of the real numbers, right? But there exists one. Okay. Okay. Cool. So let me see if I can, I'm going to end with a application of transfinite induction. I'm going to sketch this just to give you a sense of how you might prove something by transfinite induction. So here's a question. Is there a set, let's call it K, in R2, such that, or that intersects every line in the plane exactly twice? Is there a set in the plane that intersects every line exactly twice? What do you think? I mean, for instance, here's a set. Does this intersect every line exactly twice? No. Right? Okay, well, does this intersect every line exactly twice? No. Okay, well, I'll just throw more points on. Does this intersect every line exactly twice? No. You have to watch out. Like, you don't want this to happen either, because that's, there's 3, right? Remove that one. Okay, so this has kind of a funny feeling to it. Like, things are getting away from you if you're not, you just draw more lines, you add more points. How would I go about finding such a set if one existed? Maybe induction, yes. Okay, what do you think the answer to this question is? Yeah, well, yeah, of course, because I'm going to try to show you something, but it's somewhat surprising. Of course, this depends on the axiom of choice, because we're going to use transfinite induction. Nobody knows an explicit construction yet. Dylan. Well, yeah, it's kind of traditional in mathematics to warn people when you're using the axiom of choice, even though, by and large, most mathematicians these days accept the axiom of choice. It's just that the axiom of choice leads to some funny results, and so it's kind of strangely comforting to know when you're using the axiom of choice, so that you can at least be aware of it. Most people have no problems accepting it, but they just want to know, because it still has a category, it still has the status of like, a rogue axiom or something. We try to avoid using it whenever possible. Yeah. Okay. Excellent question. Okay, so here's a proof. This is a proof idea, a sketch, because I have to leave some time actually for course evaluations. So here's the idea. What we're going to do is let's call the set L, the set of all lines in the plane. Okay. How many things are in L? Uncountably many things. In fact, the cardinality of the real numbers, right? So this is called the continuum. There's C many lines. This is the cardinality of the continuum, okay? Okay, so here's what I'm going to do just to start off. I'm going to well order L. And I'm going to do so with the order type of the first ordinal that has the cardinal C. Now, it may not be the first uncountable ordinal, because we don't want to assume the continuum hypothesis, okay? So, but there is going to be a first ordinal that has the cardinality of the real numbers, okay? And by what I mean by first, everything before it has a smaller cardinality. That's important. So I'm going to well order L with the type of the first ordinal of cardinality with cardinality C. So the important thing is all before it, all elements of this ordinal, let's call it J, all elements of J have cardinality less than C. That's the important point. We're going to use this in a very crucial way. Actually, I'm going to save my time from erasing and just do that here. Okay, that's the first step. Oh, okay. So here's what we're going to do then. If I well order it, then you can't stop me from writing L as L alpha for alpha in J. So now I'm going to let my set A, the set I'm going to try to show is inductive, I'll let it be the set of all alpha in J such that there exists a set K sub alpha that basically does what I want. for the things up through alpha. So set K alpha will have property Cyclops Smiley. It'll have cardinality less than C. Second property, no 3 points are going to be collinear. Okay, so I'm going to keep it from having 3 points on a line, but it might have 0, 1, or 2. Third property, it's going to intersect, let's say this carefully, let's say K alpha will intersect every line L beta exactly twice if beta is less than or equal to alpha. So everything up to this index alpha, it will actually do the right thing for. It'll intersect exactly twice. And I'm going to do this in a nested way. So quadruple Cyclops, it's not Cyclops, quadruple Smiley. I'm going to demand that K beta be a subset of K alpha if beta is less than alpha. So here's my set. Look at all the indices for which I can construct a good set. Okay. We'll show A is inductive. So A, in fact, will be the entire set. That's the basic plan. And then we're done, right? Okay, and this is not so bad. It's easy enough to verify that 1 is in A. That is, you just let K1 be 2 points on L1. But now I'm just going to proceed like I did before with this idea, right? You first do L1 and you pick 2 points. And then you do L2, which maybe it's this. That's sort of the idea. And the hope is, okay, well, does it contain 2 points in the set already? No. Well, let's add a point. Call that K2. Okay, so the inductive step is if S alpha is in A, then I'll let K be, well, how about taking the union of all the good sets previous? That's just going to be all the sets I was considering previously. And you can convince yourself that this has cardinality C. Because basically there's C many of these and C many things possibly inside. And this follows by Smiley. And that it also has no 3 points collinear. And this follows by quadruple Smiley and Cyclops Smiley, or double Smiley. It has no 3 points collinear because it's a nested sequence here, each of which has no 3 points collinear. So you pick 3 points, it's eventually in one of the things you union, so it should be not collinear. Oh, well then what else? The last thing to notice is when you do that, well, you might be missing some points on the new line. So would you agree that all lines through K alpha have cardinality less than C? So through the existing points. So it can't hit all the points of L alpha. In other words, if you do this for all the lines through the previous points that existed, you want to know in my new line L alpha that there are still some points left to choose. Well, you look at the existing set, they don't hit every line on this point because their cardinality was too small. That's where we use the fact the cardinality is less than C. So if you don't hit all the points, well, I'll just pick 1 or 2 more points as needed to form K alpha, which is going to be K union 1 or 2 extra points. So alpha is going to be in A. And we're done. So the end construction is, let's just look at the union of all the K alphas for every alpha, and that will be the set that passes through every line twice. Okay. I need somebody. Is somebody? Oh, so that's the end of our lecture. Thank you very much. It's been a great class, and see you guys all on the internet.